All right, here we go. Welcome to today's physics video. We're going to learn today about forces and net force. Your goals are listed down here. Take a minute and read through those. Basically, we'll be learning about what force and net force are. So here we go. First of all, force. We're going to use the capital letter F to represent force. A force is just simply a push or a pull on an object. But it has a numeric meaning as well. Okay, so when you talk about a force, you can measure it. And what you're actually measuring is sort of how hard you're pushing the object. Okay, so the harder you push or pull the object, the more force you are exerting on it. Okay, the units that we can use to measure it can be either pounds, which is the non-metric, or newtons. Okay, and pounds should kind of make sense that measures force, right? Because here in the States, we use pounds to measure weight, and the idea is the more something weighs, the more force you need to lift it, right? So there you go. All right. So we will obviously be using newtons because they are metric, okay? If you want a rough conversion, 1 pound is about the same as 5 newtons, okay? Not exact, but ballpark. All right, so some examples of forces. All right, so first of all, force and gravity. All right, so when I write a force, I'm always going to use a capital letter F to tell you, hey, this is a force, and then the subscript will describe where the force is coming from. Okay, so when I write Fg, that means the force from gravity. Okay, so obviously gravity pulls stuff down toward the center of the Earth, and so that's an example of force. All right, worth noting at this point. When we did linear motion, we learned about AG, okay? So these two things are very different, okay? AG is the acceleration produced by the force of gravity, okay? When gravity pulls stuff, it makes it, or can make it, I guess, accelerate downward, right? Okay, so Fg represents the force used to produce this acceleration, okay? All right, let's see, other forces. People can push stuff, okay, right? You can have force of Roy, force of Carl, force of you, force of me, whatever. Stuff can push stuff, all right? Right now, your notebook is sitting on the table, and you are taking notes. Gravity is pulling the notebook down, but for some reason, it's not falling, right? Even though gravity is pulling the notebook down. So what's preventing the notebook from falling is this, the force from the table, right? The table is holding it up. Okay, so there you go. Now, weirdly, for the first part of the chapter here, we're going to actually ignore these two forces because in all of the examples that we're going to look at this first part of the chapter, those two forces will cancel out. All right, so for the most part, all of the forces that we're going to talk about for the first few sections of this chapter, we're going to just focus on horizontal forces, okay? And we'll ignore gravity and then whatever is holding the thing up, okay? All right, finally, and to me, this is the force that makes this chapter a little bit counterintuitive in a lot of ways, is friction. Because it's a force that's always there, but you don't always think about it, right? Okay, so the idea is anytime two objects are sliding across each other, or anytime you attempt to slide two objects across each other, friction is going to resist the motion between those two objects, okay? So here's why that happens. If you imagine trying to rub two pieces of sandpaper together, what happens is the particles of sand on one piece push against the particles of sand on the other piece, making it difficult to slide the two pieces across each other, all right? On a molecular level, this is exactly what happens when you slide one object across another one, right? The idea is the molecules from one object kind of bump against the molecules on the other object, and thus resists the two objects sliding across each other, all right? Friction will always act, this last part here is super important, friction will always act in the opposite direction that the object is sliding in, or the opposite direction that the object is attempting to slide in. Okay, so for example, if you imagine trying to pull your refrigerator out from the wall, when you pull it, you might not pull hard enough to move it, okay? And the reason it doesn't move isn't because it's too heavy, it's because there's too much friction. Now, it turns out that, in general, the heavier an object is, the more friction there's going to be. So the idea is you're pulling the refrigerator away from the wall, friction is resisting it, so the force of friction would be toward the wall, okay? Then once you get it moving, if the refrigerator is sliding away from the wall, while it's sliding, friction's trying to stop it, pushing back toward the wall, okay? So those four forces there are the most common ones that we'll be talking about. Oh, you know what I should actually add is force of tension. Well, you know what, there's a video about that later. Force of tension is basically a force from like a rope or a chain or something like that. I'm getting ahead of myself. We'll talk about that later. Okay, so some very important things that you should be aware of with forces. So first of all, if Roy pushes a box with a force of, say, 5 newtons, that's a measure of how hard he's pushing the box, and it tells us absolutely nothing about how fast the box is moving. Okay? Please, please, please do not confuse the idea of force and the idea of velocity, right? If you push on that refrigerator with, 500 newtons of force, that doesn't necessarily mean it's moving, right? So it's just how hard you're pushing it, all right? Secondly, remember that it's possible to push an object without it moving at all, right? Thirdly, even more important, or I guess maybe not more important, but more surprising perhaps, is this. It's possible to push an object one way while it's moving another way. All right, so the example I like to give is this. So imagine a giant monster or something. Here he is, he's a giant. Whoa, he's only got one eye. Whoa, I have no idea what I'm drawing here, but we're going to finish it. All right, it's a giant crab monster. Aren't you glad that you're taking the time to watch me draw this? Okay, so anyway, here's our giant monster. So the giant monster is going to throw a school bus this way. All right, so here's the school bus sliding on its side across the ground, right? Over here, oh no, a baby. That's the stroller. Okay, so the school bus is now sliding across the ground this way at the baby, right? And Superman flies down. Here he comes. Whoosh. Right? And Superman's going to try to stop the bus. Okay? So the bus is sliding to the right. Superman's going to push to the left. All right? So while the bus is sliding to the right, Superman's pushing it to the left. Now, just because he's pushing it left doesn't mean it's going to move left, right? What's going to happen is, as he pushes it, the bus will slow down, slow down, slow down, and hopefully stop before it hits the baby. And then, if he continues to push it, then it might start to move back the other way, right? If he pushes for long enough, okay? And I guess probably worth noting, even if Superman wasn't there, here, let's clean this up in a minute. Even if Superman wasn't there, that school bus is going to make a terrible sound as it slides across the ground, right? Where does that sound come from? Well, the sound of it sliding across the ground. That sound you're hearing? Oh, guess what? That's friction. Which way does friction act? This way. Which way is the box moving? I keep saying box. The bus, it's moving that way, right? So there's another example where it's moving one way and the force is acting the other way. Okay? So this is important. Do not assume if you see a drawing of an object being pushed in a certain direction, that doesn't necessarily mean it's moving in that direction. Okay? All right. Next, similar to displacement and velocity and acceleration, force includes direction. Okay? Superman can push that bus to the right or to the left. Okay? And obviously doing so changes how we think of the force, right? Okay? And as a result, number 5 down here, that means that our force can be negative. Okay? In that last example, Superman was pushing the bus to the left, friction was to the left, so those would be negative forces. Okay? Number 6, this one is really important too. When we do calculations and when we make our drawings, we're going to treat a push exactly the same way as we treat a pull. Okay? It does not matter if the object is being pushed or pulled. What's more important is the direction that it's being pushed or pulled in. Okay? So, in other words, pushing a box to the right is exactly the same as pulling the box to the right, assuming your force is the same. Okay? So, some important ideas there. All right? Now, when we did our motion section, I really encouraged you guys to make drawings, and when we did that, we drew the path that the object followed. Okay? This chapter, we're going to be drawing what are called free body diagrams. Okay? And we'll get to how to draw formal free body diagrams a little bit later in the chapter. But for now, you, at the very least, need to know how to draw a force. All right? So when you do that, to draw a force, you're going to draw it as an arrow. And most of this is fairly straightforward, but there are a couple things that are very particular. Okay? It's sort of like using proper grammar, right? Okay, so we got to make sure that we have our grammar right on our drawings. Okay, so this first one is the one that sometimes is a little counterintuitive. All right, when you draw a force, the arrow that you use to represent that force must begin inside the object that's being pushed or pulled, and then it points out of the object. Okay, your arrow should never, ever, 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 ever point into the object. Okay, so like in that last example, the school bus was sliding across the ground and Superman was pushing this way. So I drew the arrow coming out of the school bus and pointing left, right? Okay. The second one is hopefully fairly obvious. The arrow is going to point in the direction that the object is being pushed or pulled. We're going to use a longer arrow to represent larger forces. All right. Now, you have to label your forces. Must label your forces. Every force has a name and a number. Okay? So, label those forces. Don't just write 5 newtons. Write force of Roy equals 5 newtons. All right? And finally, this last one seems like an obvious one, but I see people do this all the time. If there's not a force, don't make an arrow. Okay? Suppose Superman stops pushing the bus, right? So the bus is sliding along or whatever, and Superman stops pushing it. Sometimes I'll see students do this. They'll go force of Superman equals 0. Well, remember, the length of the arrow is proportional to the size of the force. So if there's no force, there should be no arrow. Okay? So if there's no force, don't draw an arrow. All right? So that's how we draw the force vectors. Now, a lot of times our object will be moving. Okay? And so we've got velocity vectors as well. And we need to make sure that we're able to distinguish between them. All right? One of the distinguishing factors will just be simply we'll label it. We'll write, we'll label it. Okay? We'll write v equals whatever. All right? But more importantly, this. When you draw a velocity vector, you draw the velocity vector near the object, but not touching the object. Okay? So again, back to the school bus example. Here's the school bus. I drew Superman's force, right? Force of Superman. And I drew arrows underneath it to indicate the motion, right? So here's the velocity of the school bus. All right? So that is huge. Do not make your velocity vectors touching the object. Because they'll be confused as a force. Wow, sorry. Okay. And then the rest of this is fairly intuitive, I think. Your velocity arrow is going to point in the direction the object is moving in. The larger the velocity, the longer the arrow. Label your velocity vector. If the object isn't moving, just write v equals 0 somewhere near the object. Okay? So let's do a few examples. So in this one, we've got a shopping cart rolling to the west, and Roy's going to attempt to stop it. So let's see. If the shopping cart is rolling left, I'm going to draw an arrow that points to the left to indicate the velocity. All right? I guess you can put a negative on there since it's moving in a negative direction. Okay? Now Roy's going to try to stop it. So if he's going to try to stop it, that means he's going to push it to the right. So I'm going to draw an arrow that begins inside the shopping cart, points in the direction that he's pushing it, label it. Force of Roy equals, 20 newtons. Okay? So there you go. Now, in the last couple slides, I really stressed the length of the arrow. Remember, the red arrow here is the force vector. The black one is the velocity. Those don't necessarily need to be, I don't need to make the 20 longer than the 6 because they're different units, right? Newtons doesn't measure the same thing as meters a second. Okay? So, there we go. All right. Now, the next thing we need to talk about is what's called net force. Some books call this total force, all right? I tend to use the term net force. The symbol that we use for net force is the Greek letter sigma and then a capital letter F, okay? So in math, the Greek letter sigma means total, okay? It means add them all up. So, delta means change, sigma means sum, okay? Like S-U-M, sum. Okay? So net force, total force, is exactly what you think it is. It's the total of all of the forces acting on an object. All right? When you make your drawings, you don't draw the net force. Okay? You draw the individual forces, and then somewhere off to the side, you're going to write down what the net force is. Okay? So let me show you some examples. All right? So in this first example, we've got a refrigerator sitting at rest in the center of a room. So you're going to make a drawing, and you're going to find the net force. So these first ones are fairly similar, right? So here's the floor, here's the refrigerator. It's at rest. And then in the first one, Roy pulls it to the right with 8 newtons. So here's my force to the right, force of Roy, 8 newtons. Okay? So that, if you wanted it, would be this. So here's Roy. Oh my gosh, why can't I draw today? I'm struggling. So there, he's supposed to be pulling it. I'm very unhappy with that drawing. Okay, so that's what it looks like if he's pulling it. Now over here it says he pushes to the right. Okay, well that's the same idea, except now Roy's standing over here, and he's pushing it, right? Okay, but the drawing still looks the same. Remember, we don't need to distinguish between a push or a pull. Either way, his force is exerted to the right, it's the same amount of force, and it's not moving, okay? So here is my drawing. Oh, and then we got to find the net force. So in this one, there's only one force, so the net force is just 8, right? That's the only force. Oh, newtons, sorry. Okay, next. What if we've got more than one force? So here's the refrigerator. It says Roy pushes it to the right with 8 newtons. Force of Roy, 8 newtons. Now, every force gets its own arrow, always. Do not combine forces in your drawing. So there's my force of Roy. Sally is pulling it to the right. Notice I made my arrow longer, 12 newtons. Let's see, what else does it tell us? Oh, it tells us that the box is sliding this time. So the box is sliding to the right at 5 meters a second, right? It told us that up here. Okay, so there's my drawing, and then somewhere off to the side I'm going to write down what my net force is. So I'm going to do this in a little more detail than you probably need to. But this will make your life easier as we get farther into the chapter. When you to find your net force, you just add them up, right? So list your forces first. Oops. List your forces first. In this one, we've got Roy and Sally, and then add them up. 8 newtons plus 12 newtons. Okay. Now, right now this seems silly, but as we get farther into the chapter, taking the time to do this, write that expression out, will make it easier to solve the problem. Okay? So there we go. 20 newtons is my net force. Okay? All right, I'm not going to go through example B. It's exactly the same as example A, except because they're pushing to the left, my forces are going to be negative, right? So we're going to have negative 8 newtons and negative 12 newtons. And as a result, my net force will be negative 20 newtons. Okay? Thus illustrating that it is possible to have a negative net force. Okay? All right, now, what if the forces go in an opposite direction? So the math here isn't hard, but I want to make sure you kind of understand what's going on here. All right, so we've got this large box, and here's the box. It is sliding to the left at 4 meters a second. Velocity equals negative 4 meters a second. Roy pushes it to the right. Force of Roy, 9 newtons. Sally pulls it to the left. Oh no, I didn't give myself enough room to make that arrow longer. Force of Sally, negative 15 newtons. So then my net force is the force of Roy plus the force of Sally. So that's 9 plus negative 15 gives us negative 6 newtons. So that's our net force. Okay? So what does it mean? Well, first of all, it means that the total of forces is negative 6 newtons. Secondly, basically what it means is this is telling me that there are 6 more newtons to the left, because it's negative, than there are to the right. Okay? That's an important way to think about it. Okay? That in some fashion, we've got more force to the left than we do to the right. How much more? Oh, 6 newtons. Okay? So this drawing here, or what's happening in this scenario, is exactly the same as if we just had one force to the left of negative 6 newtons, okay? So this is the drawing I want. Just make sure that you understand that conceptually, as far as the box is concerned, what the box is going to do here is exactly the same as what this box would do, okay? Basically, Roy's force completely gets canceled out, and we're left with a net of 6 to the left, okay? So there we go. All right, let's see. All right, now this last example says Roy pushes to the left and Sally pulls it to the right. So here's our box. Here's our force of Sally, 18 newtons. Here's our force of Roy, 18 newtons. Negative style. Our velocity is still negative 4 meters a second. All right, and so what's our net force going to be? Well, the net force is the force of Roy plus the force of Sally. So that's negative 18 plus 18. We have a net force here of 0. Okay, so the forces in this problem exactly cancel each other out. All right, the whole next video is about what happens when the net force is 0. This is super, super important. All right, so all I'm going to say about it at this point is this. When the net force is 0, it's exactly the same as if nobody was pushing the box at all, okay? It's exactly the same, okay? Those two forces exactly cancel each other out and might as well not even be there, okay? So we will talk about that more. All right, finally, I think this is the last example here. We got a large box sliding to the left across a frictionless floor at 4 meters a second. Velocity equals negative 4 meters a second. Sally is pushing it to the right. What is Roy's force? Oh, we're missing a force now. What is Roy's force if the net force is 12 newtons? Okay, so many of you are able to just look at this and immediately know the answer. I get it. The problems will get harder though. So here's how I want you to solve these. Okay, start by writing out an expression for net force. So let's see, what are the forces acting on the box? Well, there's Sally and there's Roy. Next, plug in the numbers. Let's see, we know that the net force is 12. We know the force of Sally is 30. We don't know Roy's force. And then solve it. Subtract 30 from both sides. And you get negative 18 newtons equals the force of Roy. Notice the equation told me the direction of his force, right? Because it's negative. So there it is. Put it in your drawing. Okay? Now, another way to think about this is you could think this means the fact that my net force is 12 is telling me that there are 12 more newtons to the right than there are to the left. So if Sally's force is 30, what we've got to the left must be 12 less, right? So 30 minus 12 gives you 18, and then tack on the negative sign. All right? I believe that is it. Oh, right. Okay. So finally,